Okay, folks, we're going to chat about numbers 7 and 8 in Unit 4-2. So number 7 is about a sphere, spherical bearing. So let's start with a picture here. And the diameter is given in the problem. Now that diameter is this distance in the picture. Right, so I'll label that D here. We could also, by the way, if we wanted, we could call that a length. Whether you call it a diameter or a length, I mean, this distance is in fact, some length as well. All right, I'm going to just kind of keep that in mind for the next part of this discussion. And this is given at a certain temperature, 27 degrees degrees C. In the one I'm looking at, yours is probably different. And it says, what is the diameter if the temperature is increased to 113? So even though this is actually a three-dimensional object, we can treat the diameter basically like a one-dimensional problem. And just a little reminder here, I did this over on the right. So when we have some sort of object here of length L, and we heat it until it has a temperature change delta T, then the change in length is directly proportional to the original length and the temperature change. And again, this number right here, that's called the coefficient of linear expansion. So what we can do here is kind of apply this formula here, and I'm just going to write it like this. The change in diameter, because again, the diameter is a length, right, can be written as alpha, the coefficient of linear expansion, times the original diameter, times the delta T, which if we wanted to, by the way, we could write that T final minus T initial. And this change in diameter, you could also write that D final minus D initial if you wished. Now, formula-wise, right, I believe given, this you can look up, this is given, these two temperatures given, and the only thing left, I think, to find there is that final diameter right there. So that should get you through number 7. Reading number 8, a brass ring of a given diameter. So I got to read this again. Is heated and slipped over an aluminum bar. Okay, I might want to read that a couple of times here. Hold on. Get rid of this. So we have a brass ring. I think what I'll do is I'll draw that like so here. Here's my brass ring. And diameter, again, that's this distance, like from here to here, is given. And the idea is this has to slip over something. It has to slip over an aluminum rod. So I think what they mean here is like we've got a bar of aluminum like this, I think they mean. Again, that has a certain diameter. And what you can do is we can write one equation for the brass that says the change in diameter is going to equal the original diameter times the coefficient of linear expansion for the brass times T final minus T initial. And then over here, let's see, for the aluminum, we can write the same formula. The change in diameter is equal to alpha times the original diameter times T final minus T initial. And let me see, what is it we're looking for here? To what temperature must the combination be cooled? So we want the diameters to be the same. So let's see, this is going to be a D final minus a D initial. Let me write this out again. And then the same thing over here. D final minus D initial is going to equal alpha times D initial times T final minus T initial. All right, so solve both of these equations for this. Okay, so solve for these. Then you can set them equal to one another. And then you can solve for the final temperature. Now keep in mind that this coefficient of expansion is for the brass. This is the original diameters for the brass. This coefficient is for the, I think it was aluminum. This is the original diameters for the aluminum. Initial temperature is also given, and you're going to solve that for T final. So that one's going to be a little bit of work algebra-wise, but that should get you through it. I hope that this helps. Have a great day.